So thanks for coming to this year's Ahlfors lecture. The speaker this year is Sanjeev Arora. He's a professor at Princeton University and also a professor at the Institute for Advanced Study. He worked on this computer science and theoretical machine learning. He received a Pegger Fellowship in 1997 and the Simons Investigator Awards in 2012. He also received the Goldell Prize twice. And also he received the ACM Prize in computing and also the Fulkerson Prize in discrete mathematics. And he's a member of the National Academy. And his work is most famous for his work on computational complexity and the probabilistic checkable proof, including these famous PCP theorems. And so we are very happy that he will come to give this year's Ahlfors lecture and to tell us about the mathematical machine learning, which I think all mathematicians are very interested in and want to know, find out the answer. So thanks a lot, Professor. Thank you.
Should I turn it off? Should I turn it off? Well, thank you. It's a pleasure and honor to be here and to tell you about machine learning. And this talk is, it assumes basically no prior knowledge, and it's an introduction to machine learning. And if you happen to be at ICM last month, it is basically the same talk. So, okay, so machine learning. Oh, I didn't turn it on. Yeah, machine learning is a new kind of science. And these days, as you probably know, computers can play Go better than humans, spot certain kinds of cancerous tumors, and are approaching human ability in translating languages and driving cars. And so it's been in the news a lot as a hot technology. But in this talk, I'll make the point that it's also a new kind of science. And it's a science of creating machines and programs that can improve from experience and interaction. And notice that this definition doesn't say anything about human intelligence. Imitating humans is not an explicit goal. And indeed, for the foreseeable future, we expect that on certain tasks, machine will be much better than humans. And on other tasks, they might be worse than a toddler. And once you start doing these tasks or trying to solve these tasks by machines, you're forced to encounter some very basic, even naive questions like, what is learning? What does it mean to understand the world? So for example, what makes a sequence of pixels correspond to a scene with a pedestrian? Something that you hope that your self-driving car in 5 years would know how to solve. And these are simple, even naive questions, almost at the level of Newton's question of, why does the apple fall from the tree to the earth? And when people first heard it, they said, what do you mean? That's what things do. So these are naive questions like that, and that's always the beginning of a good science. And so this talk is meant to be an introduction for a mathematical audience to this science. And it has the following parts. The first two are the main ones. I'll give you a mathematical formulation of machine learning as it exists today. And the second part is some examples of machine learning in action, including unsupervised learning and sequential decision-making, game playing, et cetera. And part three is a brief one, which is need for mathematical understanding of deep learning. This is really a trailer for my talk tomorrow on deep learning. And then part four is just conclusions. And it's meant to be an easy, approachable talk. It's a tour with many stops. And it's OK if you don't follow any individual slides. Probably you'll catch up again in a slide or two. So first part, mathematical formulation of machine learning. So operationally speaking, machine learning boils down to learning patterns in data. That's the paradigm today. The paradigm in this field has shifted over many decades in many directions, and I won't sketch that history today, but today, this is the pattern. This is the paradigm. And what does that mean? We often hear that term, learning patterns from data, and the basic mathematical idea is pretty simple and has been understood for at least a couple hundred years, if not longer: curve fitting, something we learned in high school, fitting curves to experimental data. So here's an example of data about inflation and employment over a certain period in Japan. And you squint at this curve, and you say, well, it looks kind of like a straight line. And indeed, that straight line is called the Phillips curve. Now, that's actually a somewhat controversial idea, and some people doubt if that curve exists under all conditions and so on. But anyway, the main point here is that this curve was fitted to data. Here's another example. It's not a curve, it's a surface, right? Pressure, volume, temperature, and mass of a gas. They're related according to this. And this relationship was found by fitting a surface to the experimental observations, and they allow you to predict any one of these quantities given the others. So this is a gas law. Now, of course, it was experimentally discovered, but then one of the crowning jewels of early statistical mechanics was to explain this law. But in general, we're interested in curve fitting to experimental data. Now, machine learning uses also this kind of surface fitting or curve fitting, but with many more variables: millions, tens of millions, hundreds of millions of variables. And that's fitting this curve to data is like finding the patterns. So let's see a very simple example: learning to score reviews, movie reviews. So here are some reviews for this movie, actually by a Harvard alum, Damien Chazelle, La La Land. So here are some movie reviews I found on Amazon. Slow moving, couldn't get into this movie despite all the awards it has won. And here's another one. Wow, did not know what to expect and was delighted. Loved the homage paid to the musicals of old. Now, if you give these reviews to a human, they can assign a numerical score. So let's say the numerical score assigned to that one is minus 1.5, and to this one is 2.5, on a scale of minus 3 to 3. So now the learning task is you're given reviews like this, text reviews, and the human rating score. And your task is to learn to predict the rating score given the text of a new review. So now, given all the build-up with gas laws and so on, you might wonder, OK, what's the law of movie score reviews? Well, clearly the law is going to be something very complicated, right? It involves all kinds of prior knowledge about movies and language, et cetera, et cetera. So the law is not going to be a simple one like gas laws. But you can start with a simple law and see how well it fits. So the simplest law you would come up with is what's called a linear model. And the law asserts the following, that, OK, so there are 100,000 words in the English dictionary, give or take. And the law is hypothesizing that we humans, when we assign a rating to a movie review, are walking around with a sentiment score for each word. So for each word W, each one of these 100,000 words, there's a sentiment score theta sub W, which is a scalar. And the review score for a review, which has many words, is just the total sentiment score of all the words in it. Now you can normalize this and make it lie between minus 3 and plus 3, but for now just assume it's the total sentiment score. So it's a very simple linear model, because it's just summing up the sentiment score of words. Now, of course, we don't know these sentiment scores. So what are these sentiment scores that we people are walking around with in our heads for these words? Well, finding the sentiment score for each word is some kind of a surface fitting with 100,000 variables. So it goes as follows. Theta sub W is going to be a variable. And you're going to do what's called the least square fit, which you may remember from high school, to this. So You're given a bunch of reviews. Each has a score. So this is your training data. And theta sub w is a variable. And you're trying to find an assignment to the theta sub w's so that this sum of theta w for the reviews that you're given correlates very well or is very close to the review you're given, the score you're given. And you do a least square fit. Namely, you minimize this sum of the squared differences. So this is a Gaussian least square fit. You're finding a 100,000 dimensional hyperplane, something you didn't do in high school. But it can be done in seconds on a modern computer. Is there an echo of some kind? Does it have to be off? It is off. OK. Sorry? There is an echo, right? Yeah. OK. So just to give you some sense for what the solutions look like. So I asked a student to take movie reviews and fit a model like this. And he gave me these scores that he came up with, or the solution had. And so if you are given a review like this, you read up the scores from this table, the scores that were found by the fitting. And you take those numbers and you add them up, and you get 2.7. So that's the score of the movie. OK, that's the predicted score according to this model. So after you fitted the model, you can now predict scores of new reviews that you're given. So you look at this table and you see, OK, so good has a high score, loved has a high score, right? So and then some words are neutral; they have a low score. So you realize that the discovered patterns in this case are just how much words correlate with the positive score, right? Loved is in more reviews that are positive, so the model will assign it a higher score. Okay. So this is what this is the way in which model fitting or curve fitting picks up patterns in data. Now this for a simple model. In the complicated models we'll talk about very soon, it's not so easy to see exactly what patterns are fitted and what patterns are discovered, but the model ultimately is finding them. So which brings us to the definition of what machine learning today does, which is it finds a suitable function, which we call a model, given examples of desired input-output behavior. Okay, so there's some inputs in the previous example, movie reviews, and which you can think of as a vector, right? Which words are in there? That's some kind of a vector. And the output is the desired score. So input is given to the model, output comes out, and x and y are the desired input-output relationships. So examples of inputs and the desired outputs. So in the previous example, the desired input-output behavior was you input this review text, represented as a vector, and out comes a score, okay, out of this model. And this model has some trainable parameters, theta. And in the previous example, theta just consisted of this vector of scalar values for words, one for each word. So this, given a review, the model outputs the sum of the sentiment scores for the words in that review. So that's the output of the model. And the desired output is the human score. And so the training method was to take some examples where the human score is given, and then you fit this model by minimizing the sum of squared differences. Okay, so that's on the left-hand side is a general paradigm. Okay, this is a very simple linear model, but in general, inside that black box, which is marked theta, could be something more complicated. It has some trainable parameters, theta. So that's what machine learning does. All right. So now the formalization is that when given an input x, the output of the model is f sub theta of x. It depends on its internal parameters. And the desired output is y. And so this model is just minimizing this so-called loss function, which is the sum of squared differences between the real output and the desired output. Now, this is just a very simple subcase. You can have other loss formulations, et cetera, but that's the general idea. Okay, you can measure this difference between the true output and the desired output in other ways than L2 norm. Okay, so so you train this model on some data that's provided, and now it's expected to do well in future. How's that argued? And this is a framework that's derived from statistics, classical statistics. And the assumption is that this data, the x, y pairs, are drawn from a probability distribution. So in this case, for example, the distribution on pairs of movie reviews and their human scores. Now that can be a tricky philosophical point because there may not be such a distribution, right? Because new movies are coming in all the time, and then fashions change, et cetera. So there may not be a single distribution out there, but that's the assumption, that movie reviews are drawn from a distribution, a fixed distribution. And the training is optimizing this loss on the samples, and the testing will take new x's and see how well they predict the missing y. So you're given just x and not the y. This may sound a little complicated, but in practice, all that happens is you're given some amount of data, you take 80% of that, let's say, for training, and now you see how well that trained model predicts on the remaining 20%. So that's the framework of machine learning in a nutshell. Now, this formal framework can be modified and adapted to all kinds of other settings, as we'll see. Now, one comment for mathematical audiences. So you're trying to learn some functionality, some behavior mapping x to y, and you're trying to learn it from examples. Well, the object in classical mathematics that I can think of that's most analogous to this is harmonic analysis or Fourier analysis, which also allows learning a function x as f from examples of x and f of x, under reasonable assumptions on f and the data and so on. So that's the closest analog I know of. And the trouble is that it's infeasible for this problem. And in general, that's true for a lot of classical mathematics, because the dimension here, n, the dimension of the input, the number of coordinates in x, is large. Let's say 10,000, which is not so large if you think about, say, classifying images. That's only 10,000 pixels. That's cameras have millions of pixels. So 10,000 is not even very unreasonable. But that's already very large for classical mathematics because, for instance, for Fourier analysis, if you apply this algorithm for learning functions using Fourier analysis, you would need resources that are like exponential in n. An exponential of 10,000 is a gigantic number, more than the number of elementary particles in the universe. So exponential of n is completely infeasible for anything. So that's why the classical ideas that I know of don't work, and you have to do something new. So now you might be thinking, oh, so what is this amazing new analog of Fourier analysis, very efficient, that machine learning has come up with that's used to train these models? Well, the answer is a little bit of an anticlimax. It's just gradient descent. OK, so in all of these settings, this desired, the model is some kind of a continuous or even differentiable function, the loss function. And you just use gradient descent, which is also another algorithm you may have seen in that we also teach in freshman calculus sometimes, which is that the gradient is the direction of maximal change, and so negative of the gradient is the direction where the function is decreasing the fastest. So you start with some arbitrary theta 0, or say a random theta 0 often, and then you just move a little bit along the direction of negative gradient, which reduces the loss a little bit, and you continue. So very simple and trivial algorithm. People also think it's a natural algorithm. So it may seem kind of naive, but actually there's a mystical belief that actually this is a very good algorithm. And if you think about it, that's the way we also run our lives often, right? Like you're not feeling well, you want to improve your life, you try a new diet, you try a new exercise schedule, or whatever, right? You make some simple change, and then if it makes you feel better, you can stick with it, otherwise you try something else. So it is a kind of natural algorithm. People say that evolution is doing something like that. Many natural systems are doing things like this. So it's a natural algorithm. Now, the complication in machine learning, especially in deep learning, which we'll talk about in a minute, is that this loss function is non-convex. And as in many other settings in mathematics, convexity in optimization goes hand in hand with ease of use, efficiency, etc., nice properties, and non-convexity goes with trouble. So a priori, you wouldn't expect that this simple algorithm would work for these very complicated non-convex optimizations, but actually it does work in practice very well. Okay, so yeah, this is convex versus non-convex. And in convex, gradient descent does come down to the best solution in finite amount of time. But in non-convex, because there are these ups and downs, it's not even clear that gradient descent is the right algorithm. But nevertheless, in practice, it seems to work well. Now, just as an aside, even vanilla gradient descent works pretty well. But in practice, people soup it up with various tricks. So for instance, you can vary the learning rate, this eta, the step size. You vary it over time. That turns out to be very crucial. You don't move along just the current gradient, but also you keep some memory of the past gradients. And you move along some combination of the past gradient and the current gradient, which is called momentum. There's something called regularization. So there are other tricks which we won't talk about today. But what I do want to bring up is deep learning, which is a very simple subcase of the framework that we just saw. So instead of a linear model, you have now a nonlinear model, and it's multi-layer. So this is a simple case of deep learning, and from now on, I'll have occasionally these asterisks as in up there, and these are meant to be footnotes, which is caveats about whenever I'm being simplistic or hiding some details, etc. But at least in this simplistic model, a deep net is very simple. In the earlier model, we had a linear model. Now you have linear, so you have an input coming in. You apply a linear transformation, which is a matrix, M1. Then you apply nonlinearity. Then you apply linear transformation, then a nonlinearity, linear transformation, etc. And people have tried all kinds of nonlinearity, but today, the kind of nonlinearity we do is something very simple, with some simplification again. It's just the following. Given a vector, you just zero out the negative components of the vector. So it's piecewise linear. This is called the ReLU nonlinearity. Okay, so that's the matrix. It's multi-layer. You apply linear transformation, zero out the negative coordinates, apply another linear transformation, zero out the coordinates, etc. So that's the model. And the parameters of this model are these matrices, M1, M2, etc. Was there a question? And as usual, there's training data. You're given examples of the input and the desired output. And this model produces some f sub theta, where theta is this vector containing the entries of the matrices. And you find these entries of the matrices by just minimizing this loss function. Now, unlike in the linear model, this loss function is complicated because it's this multi-layered computation. So theta has many layers, and some parts of theta apply first, and second part of theta, the third part of theta, etc. So it's a multi-layered model. And how do you, in order to train that, you need to compute the gradient. How do you compute the gradient? You use a chain rule, okay? Because you have a composition of functions, and you can compute the gradient by the chain rule. And you can do chain rule in the naive way, and that would be fine, but it turns out to be slow. And there's a very nice algorithm from 1984 called backpropagation, which does this faster. Okay, it applies a chain rule in a more clever way. So that's it. That's deep learning in a slide. We introduced machine learning, this basic paradigm, and then instead of the model, right, this black box, I have now this multi-layer model, which maps inputs to outputs. All right. Oh, I thought I did this. What happened? OK. So why this simple model? Turns out, over the decades, people tried various kinds of other models. And after many decades, people have found that this is the simplest kind of nonlinearity that still seems to work. And because it's almost linear, it sort of allows quick optimization on today's computers using today's algorithms, okay? Because this gradient behaves nicely, et cetera. So that's sort of the reason why the field has settle upon this. But it's provisional. Maybe in 5 years, there'll be something new. So summary so far, machine learning involves finding patterns in data. And finding patterns is some kind of a surface fitting involving millions of variables. And we saw this training of the model with the desired input-output behavior. Why did it take off in the past decade? It's some kind of a virtuous cycle involving availability of data, some new algorithms and hardware like GPUs, which weren't available 10 years ago, which have put the power of supercomputers on the desks of grad students, and of course, commercial payoff. And there's a virtuous cycle because once you have commercial payoffs, that money feeds into the other two. So that's the introduction to machine learning. And now I want to show you how to use this framework to apply it to some other settings. And the key idea is to still stick with this paradigm I showed you, fitting a model to desired input-output behavior. But we are going to apply it creatively to some other settings. And again, if this was already not a caution, it's very simplified and simplistic. So let's return to that example of assigning a score to movie reviews. And we had the simple linear model. And when people see it, and our undergrad, we teach it in basically the first week of undergrad machine learning, they see it and they say, well, this is very simplistic. Well, firstly, this is not how we humans do it, right? Because word order in text matters, right? No good means something very different from good, no, right? But this model is just summing up the sentiment scores of words, so it assigns the same score to both of them. So clearly it's wrong in some cases. And the other thing they say is that we don't need to see millions of examples of earlier reviews, weighted reviews, in order to rate future reviews. The very first Amazon review you saw, you could already, as a human, assign it a review score, right? Because you understand language, right? And so somehow, if you understand language, you don't need to be told how to rate movie reviews, right? You sort of know already. So how can machines understand language? Now, there's a long history of this going back to the ancient Greeks who invented propositional logic and then all kinds of other things like Chomsky grammars, model theory, et cetera, which try to formalize the meaning of language. And the field did try to use these for a long time in trying to write programs that understand language. But today, the dominant paradigm is what I showed you, using a model. And that's what we'll see next. Okay? How can machines understand language? And this is the field of unsupervised learning, where there are no human-supplied labels. Okay? So the machine is just given a ton of language, let's say Wikipedia, which has billions of words. And after reading that, it somehow understands language, whatever that means. And so the idea is that you use a large corpus, text corpus like Wikipedia, and train the model on just that. And what's the training? You train the model to predict part of the text from the adjacent text. So to put it simplistically, sentence completion, something that your cell phone has to do when you're texting, right? It tries to complete your text. So the example sentences, I went to a cafe and ordered blank. Now, a reasonable completion could be coffee or croissant, and puppy would not be a reasonable completion. So the idea is going to be to train a model to learn to do such completions using a huge amount of text. And in the process, if your model learns to do this, it must implicitly pick up on grammar, that the next thing is going to be a noun, common sense, that you don't order a puppy at a cafe, etc. Right? And this is called unsupervised, but it's really, the way to think about it is that the supervision is in the data. There's a ton of data that humans produce for some other purpose in Wikipedia, and you're using that to train the machine. It's a very powerful paradigm. And these language models are used, as you can imagine, in machine translation, question answering, et cetera. So how does this language model work? So we're trying to train it to predict the next word. And it has some parameters. We'll return to that. But it's given the last 5 words, let's say, W1 through W5, and it's trying to predict the next word. So obviously, it can't predict the word exactly, but it's going to output a distribution on all English words, on all 100,000 English words. So for instance, coffee may have a probability 40%, croissant may have a probability 30%, and then puppy should have a very low probability. So how does that work? That sounds a little bit bizarre, that it has to output a distribution on 100,000 words. But let me point out that you are used to this, actually, each time you look at the weather forecast, right? It also outputs a distribution, albeit on a small number of events, like rainy, sunny, cloudy, etc. And the difference here is that it has to output a distribution on 100,000 events, right? These 100,000 English words. But the idea is the same. And in this case, the model, this is a very simplistic model, word2vec. And the idea here is that it's trying to output this distribution in an implicit way as follows. So it has a vector inside, so as a parameter in there, a vector for every word. So these are trainable parameters. And this vector is 300-dimensional, which is nothing special about 300. It's sort of like large enough to let it represent many shades of meaning. And that vector represents meaning, okay? And the meaning of the word. It's going to learn that meaning. But along the way, its provisional way of predicting the next word is that it has some understanding of word meanings, these vectors. And given the last 5 words, the probability of the next word, being W, is proportional to the exponential of the inner product of the vector of W, VW, the vector of W, with the average vector of the last 5 words. So these vectors are its parameters, the trainable parameters. So this is in the form of some statistical physics models. There's exponential description of the distribution, and there's an implicit normalizing constant, which I'm ignoring, okay, also in the notation. In the full treatment, you have to not ignore that. So now what's the measure of goodness of fit? Like as in the weather forecast, if it's a 60% chance of rain and then it doesn't rain, it's not that it was incorrect, just that if it happens over time, you would know that it's not doing something right. So the idea is that you do something similar. So you train this model by sweeping across Wikipedia, and you're trying to make sure that it assigns a high probability to Wikipedia, which is its notion of normal text. And so the loss function is the reciprocal of the probability it assigns to Wikipedia, according to this model. And how do you compute that probability? By factoring, using Bayes' rule. So we know that as you sweep through Wikipedia, the probability of the ith word depends upon the last 5 words. So you factor it out like this using Bayes' rule. And then you get this expression like this. Okay? Again, ignoring the normalizing constant. And now this is some differentiable function of the parameters. And you do your usual machine learning paradigm. You start with some random assignments to the vectors, so random vectors. Initially, the model knows nothing, and it trains on Wikipedia. And by the end, it's predicting well, and then it has learned the meaning of the words. Okay, so those vectors capture the meanings of words. So that's the idea. So you see, it's a very different setting, but somehow it fits in the same paradigm of fitting this model with desired input-output behavior. So once you learn these models, what are the properties of these vectors, you might think? So for example, turns out that this model, the vectors it learns, the cosine of the angle between those word vectors correlates with human notions of similarity. So if you ask humans to rate similarity of words, like lion and tiger, people say are fairly similar words. They're on a 0 to 1 scale. And lion and coffee are very different words. So if you ask humans to give a similarity score from -1 to 1, then the cosine of the angle between the corresponding word vectors correlates pretty well with these human similarity ratings. Turns out you can also use word vectors to define in a very simple way sentence and paragraph vectors that capture sentence and paragraph similarity. So human ratings of similarity of sentences or paragraphs, short paragraphs, you can also capture using word vectors. That was there have been some papers, and there maybe a good one is this SIF embedding that we did a year ago. You can incorporate these semantic vectors, the word meanings, into the movie rating task and improve it a bit. So that's possible too. An exciting recent discovery is that if you look at word vectors for different languages, English and French, say, well, you would say that English speakers and French speakers are basically talking about similar things, right? We have a similar world. Okay, they have more cheese or whatever, but basically it's similar things. So it turns out that you can align the word vector spaces between English and French, in a completely unsupervised way so that that alignment, the linear alignment, actually makes sense. That's a very amazing discovery in the last year, which has gotten people very excited about the possibility of being able to translate, which it can do in some rudimentary way, even without knowing any examples of translation. Experimental, yeah. Some of the other things I talked about, there's theory, but not this last one. From this slide, I want you to bookmark that comment about sentence and paragraph embeddings, because we'll need that before the end of the talk. All right. So predicting review scores, passively understanding word meaning, etc. Okay, so we've used machine learning for that. But students want to know today, well, how can machines actively interact with the world via a sequence of intelligent decisions? Because clearly that's what intelligence involves, right? Or not to mention even Go playing. So, or driving a car. So you have to interact with the world and not have this kind of static kind of learning where there's an input and an output. So can you adapt this paradigm I just showed you to do this? Now, again, there are 20th, the framework I'll show you has some 20th century antecedents. So in probability theory, you might have seen sequence of actions being taken, for instance, in analysis of betting and gambling games, so martingales, for instance. In economics, these ideas have been known, for instance, managing stock portfolios, playing repeated games, prisoner's dilemma, etc. So those are sequence of decisions. Control theory, of course, controlling a power plant or some other complicated system, again, involves a sequence of decisions. And what we'll talk about is descended from that. So this is a sequential decision framework that machine learning uses today. And the idea in sequential decision making is that when you make the very first decision, you have at the back of your mind how this will all play out in future, right? The possible scenarios that could develop in future. So you're always working with a tree of possible actions and interactions, okay? And this includes actions by the opponent or the environment. And these actions can be stochastic. They could be a distribution of actions. And so this is really a tree, okay? An infinite tree potentially, and it blows up. It's very large. So for convenience, for the remaining two slides, I'll only talk about game playing. So in game playing, let's say Go, there's two players, and there's this tree of all possible actions. And at the end, you win or lose. So let's say you have a loss of 1 if you lose the game, and 0 if you win. So you're trying to minimize your loss. And so your very first move is what? Well, it should be the move that minimizes your expected loss, right? Assuming your opponent is stochastic in some way. So that's the framework that 20th century science and mathematics has used. Now, the practical difficulty in applying this to machine learning is that, of course, this tree is too large to allow full exploration. So you cannot define the optimum decision at the first step. So you may remember the chess playing software, which was already pretty good and world champion by the 1990s. And the idea there was the decision maker is a list of handcrafted rules, which you got a bunch of grandmasters and computer programmers together in a room with a large database of old chess games, and they came up with these rules. And they had some kind of a way of evaluating algorithms. So the handcrafted rules cut down on the set of possible next moves. And then among the 5 or 10 or 20 moves that come up with from this analysis, you use a move evaluation algorithm to evaluate those moves and take the best one. And this move evaluation algorithm can't obviously explore the entire tree. It's too large, but it does some kind of limited look ahead with some approximation heuristics. So that was the framework in 1990s, which maybe many people may remember from that time. And so now we want to adapt this to this modern view of learning from data. And so the list of handcrafted rules goes out. That currently doesn't fit in the paradigm, although it's a nice research problem to incorporate human input. And instead, you replace the handcrafted rules with what else but a model. A parametric model that's going to, given this current situation, output a distribution on the next move. And in training this model, we'll still need this move evaluation algorithm. So that's the framework. Okay, so we have this kind of sequential decision-making framework, and we are going to define this model which replaces this human decision maker. So now this model is the decision maker in this tree. And what's this model doing? Given some board position, which you can think of as a vector, is going to output a distribution of moves. Completely analogous to the word or the language model that I talked about. So, and this decision model is going to be applied throughout the tree. And how do you train this model? Okay, so initialize. So you're going to use the standard paradigm. You initialize with some random values of the parameters, which are meaningless, and then you train it by minimizing the expected loss. And you use your move evaluation algorithm, the approximate move evaluation algorithm, to estimate the loss. Okay, so don't try to think of what's inside the model. It's just a model, and you're going to define the loss function, and then you can train it by gradient descent. And this loss function is just, given the current value of theta, you give it a move, and there's a distribution of next moves that it gives you. Sorry, you give it a board position, and it gives you a distribution of next moves. And using the loss evaluation algorithm, you evaluate the expected loss, and that's your loss function. Just one move at a time. Yeah. So of course, okay, I'm suppressing the detail that this loss evaluation algorithm also uses deep learning, which I'm not. So you also improve in the actual method. You improve both the loss evaluation algorithm and the next move algorithm using the same kind of training. Okay, but abstracting that away, once you have a loss evaluation algorithm, you have this loss function, and now you can use gradient descent to train this. How? Well, it uses the fact that once you can evaluate a function, you can estimate the gradient. Okay, so why? Because here's a crude method, and warning to all the young, smart students who might try to immediately go home and try to implement this on your computer. Well, this is a very crude method. People don't do that, and a lot of research is in getting better methods to evaluate the gradient. But the crude method would be that suppose you know how to evaluate the loss function. So I input any theta, and I can estimate the loss. Well, then I can evaluate it at theta, and I can evaluate it at theta plus eta, where eta is some small noise. And if I do it that way, well, I know that L of theta plus eta, by just expanding by Taylor's approximation for small eta, is something like L theta plus eta times the gradient. And so if I evaluate from a few enough random etas, I can read off the gradient. Okay, so if you can evaluate the function, you can estimate the gradient. Now this is very noisy, but okay, you can estimate it, and so you can do gradient descent. So that in a nutshell is the idea. Okay, so this basic paradigm of having a model can be flexibly applied to all these different settings. Okay, so I've shown you how these frameworks apply to various settings, and part 3 is really a trailer. In my original talk, there was a little bit more at ICM, but this is a trailer for tomorrow's talk, which is need for mathematical understanding of deep learning. So we already saw this. The deep net is like this, and the parameters theta is the sequence of matrices. And then this output f theta, and therefore the loss function, involves some kind of a chain of operations on these matrices, and that's non-convex. So some key questions. When and why does gradient descent work, and how fast? And as I already mentioned, this is a non-convex loss function. Why deep and not shallow? So you could define this, this architecture with 2 layers, 20 layers, 200 layers, 2,000 layers. People have done all of that. Okay, and deep actually generally helps if you do it the right way. So why does it help? Well, it's, we'll see some reasons next time. Here's a very interesting question. Why doesn't training overfit to training data? Now, this is an issue in classical statistics about the difficulties you have when you use a very complicated model. This is related to the millennia-old notion of Occam's razor, right? Like simple explanations are best. So, so it turns out that today's deep nets have tens of millions of parameters, which is actually, we have a lot of data, but that's still more than, even in many settings, the number of data points, much more than the number of training samples. And so, and in fact, these deep models have so much parameters that they can actually fit even random data. Okay, so data that has no patterns at all. So classical statistics says that that's a bad idea, because if you think about even the simple model we saw about the Phillips curve between inflation and unemployment, you stare at this data and we said, okay, maybe a good approximation is a linear model. But of course, you could do this curvy model, right, which fits the data even better. Of course, it is not a linear model. It is higher degree, right? It's a curve. But it fits the training data even better. And that's called overfitting. So the problem with this model is that it won't predict on future data. So remember, our methodology is that you reserve 80% of the data for training and 20% for testing. It won't do well on the test data. So somehow this was a no-no, right? We've known this since the time of Occam, who said simplest explanations are the best. But today's models fly against that recommendation. The number of parameters is way more than the number of training samples. So in principle, they are capable of doing exactly this. And this paper about the training models and random data with no structure at all shows that they're capable of doing that. But somehow when you give them sensible data, they don't do this. They do something meaningful. So explaining that is a very nice question. And also how to interpret the trained models' inner workings. With a simple linear model, you can sort of point to variables and say, this is what that variable is doing. But in a complicated multilinear network, there's no such explanation, and there's some work on that. So these are some key questions, that some of which we'll talk about in tomorrow's lecture. So just to give you a taste, so analysis of optimization. So the first hurdle is that non-convex optimization is NP-hard in general. Okay, so this is from my long background in computational complexity. You know, this is a basic tenet in computational complexity. Basically, any sufficiently complicated optimization is NP-hard. Hurdle 2, loss of L theta is essentially a black box to us. Now you might be thinking, wait, black box? Why a black box? I wrote down the loss function for you explicitly. Everything is known here. The form, the functional form of this expression, the x's and the y's, the data and the labels, everything is known. What's unknown? What's black box? And the black box is that we don't have a good mathematical description of the data x, y. Because data is like, you know, what makes a bunch of pixels an image of a dog versus an image of a cat? There's no simple mathematical model of that. And so these are kind of like unknown things in our cost function. And so if you want to prove a theorem, right, about some mathematical object, you at least want that object to be well defined. And we don't even know a definition of what makes an image of a dog versus a cat. So, yeah. No, I wasn't talking about black box access. Yeah, I will do that in the next talk. But yeah, well, I'm just saying mathematically it's a black box, right? So what I'm contrasting with is the following. So maybe there's some applied mathematicians here. And there's a tradition in applied mathematics, certainly in recent years, that you work with data as follows, that you have a model, like mixture of Gaussians or some such explicit model for how the data was generated. We don't have any such model. So if you don't even know what the data model is, how can you have a theorem saying my algorithm works? You don't even know what x and y are mathematically. So that's my point. It's a more fundamental problem than even analyzing optimization. So yeah, indeed, the analysis is that you treat this function, the loss function, as a black box. You can evaluate it at any point theta. You can evaluate the gradient, but we don't know anything else. So, with that framework, treating it as a black box, you can make some kind of analysis. It's not as compelling as you would like. But the black box analysis is something like, Well, so long as gradient is non-zero, by definition, there is a direction such that if you move in that direction, the loss decreases. So there's a descent direction. So fine. So you can keep descending. And clearly, this method, the fixed point would be that the gradient becomes 0. So at least locally, you can't improve the function. But this is not quite right, because we're not moving infinitesimally. We're moving a finite amount. So if the Hessian is large, right, this function is oscillatory locally. And so if you make a small finite step in the direction of the negative gradient, you move there, and you find, oh, the loss didn't decrease. Why? Because the gradient was changing so much. So at the starting point, the gradient was pointing in this direction, or negative gradient. But as you moved along, even a small amount, the gradient has completely shifted. So you didn't end up reducing the loss. So to ensure descent, you have to take small enough steps determined by the smoothness, the norm of the Hessian. And then you're guaranteed to get close to a point with gradient equal to 0. And the speed is determined by these, the norms of these numbers, the gradient and the Hessians. And that's called a stationary point. Now, that's one solution notion, but you can have more complicated solution notions, like second-order local minimum, which is like a local valley. And turns out there's a related analysis which also shows that you can achieve that. So that gives you a taste of the kinds of things people are doing, and maybe we'll talk about more tomorrow. Analysis of non-convex optimization, I'll probably skip that. There's not much I'll say here, but this, as I wanted to say, fits a little bit more in the framework of applied mathematics that you may have seen, for instance, Helsinki problems, or what are called inverse problems. You assume that data is generated according to some clean mathematical model, and then the optimization landscape is understood, and then you can prove theorems. Why no overfitting? We'll discuss this too tomorrow. And the popular conjecture is that these neural nets, even though they have a lot of parameters, those parameters are not all free. And by some magical property of the data or of the training method, these parameters end up being very interdependent. For instance, they rely on a manifold of much lower dimension. And in the next lecture, we'll see a partial realization of this suggestion. And what we did was that we looked at empirically at a lot of trained neural nets, deep nets. And we showed that properly trained nets have a property called noise stability. And we prove a theorem that nets with this noise stability property, we can show that their parameters lie in a lower dimensional subspace. So not just on a manifold, but on linear subspace. So that effectively reduces the number of parameters in the neural net and gives some estimates better than previous methods for the capacity of the neural net, the number of parameters. So taking stock and wrapping up. So we teach this machine learning, basically whatever I've told you in undergrad courses. And some of the reactions are that students are surprised. This is just mindless model fitting, right? You're just fitting this model, input-output behavior, to various settings. And they say none of this is remotely how humans think. And there's some answers to that. So one is that the imitation approach has not worked so well in the past, right? Like until a century ago, the only flying objects we knew of were ones that flapped wings. But of course, a machine doesn't need to flap wings to fly, because there are things like jet engines, which nature doesn't have. So you can do something very different once you don't have the constraints of nature. And in fact, you would argue that the advantage of machines is precisely that they can crunch data, that they can do billions of operations per second, or tens of billions of operations a day. So they leverage it's like their jet engine, right? And maybe they'll develop actually in a very different way, that the kinds of tasks they are good for are very different from what this brain is capable of. And finally, and most seriously, we have very little idea at an operational level how humans think. This is the most serious problem, because we really don't know what's going on inside there. And of course, neuroscience is a hot field today. And the main tool being used there is machine learning. It's the best hope for figuring out how humans think. And so I want to end with something I was involved with. There are many people who are applying machine learning to neuroscience, and I just want to give you a taste for how these things that I showed you come together. So this is a sample task of looking inside the brain of a person who's fully conscious and thinking. So this person is sitting in an fMRI machine and watching a movie, Sherlock Holmes. And the fMRI machine, what it does is it measures blood flow at, say, 50,000 points in your brain. Okay? And from that, you're trying to get some sense of how the brain works. Now, like you, probably many of you, when I first saw this, I said, this is ridiculous. You're trying to understand human intelligence, not fluid mechanics. What does blood flow tell you about intelligence? But then if you think about it and you talk to colleagues, you realize that it's actually not so crazy. Because we do know for a fact by now that different regions of the brain are involved with anger, love, excitement, different human emotions. And probably there are, again, hundreds of other micro emotions that we don't even have names for. And so this 50,000 dimensional vector of blood flow at every point is some kind of a crude sketch of your emotional profile as you're watching this movie, right? And so, OK, so that's your raw data. And now you want to relate it to the stimulus that was being presented, which is a movie. Now, the movie is a very complicated stimulus, right? There's explosions, there's all kinds of dialogue, and moving pictures, and so on. It's a complicated stimulus. And in order to relate it to this very simple thing, which is a vector, which is called a voxel vector, we need a simpler representation of the stimulus. And so my colleagues at Princeton had the idea of annotating each movie scene every 5 seconds with a human annotation of 2 or 3 lines. So something like, Sherlock and John are talking about the murder in an old room with Mrs. Hudson. So that's an annotation of a few seconds. Things like that. So now we replaced it with this text every 5 seconds. And you also have this voxel vector every 5 seconds of blood flow measurements. And now you're trying to relate the two. Relate in the sense of, figure out where is the thinking happening or the human response, the reaction, and so on. So that's a problem my colleagues came to me with. They put this language there, and they had some idea that these are their machine learning models for language. But turns out there isn't any model out there. There wasn't any which could work with this small amount of data and come up with a reasonable language model. And that's why we developed this model I told you about, which I asked you to bookmark, expressing the sense of a sentence or paragraph. We developed it for this. So we did that. So we want to decode, and we did that. So you want to decode in the following sense. So you want to relate them in the following sense. So you want, let's say you have these annotations for 5 time steps, and you scramble them. And now you want to say, and you're given the corresponding fMRI responses, and now you want to set up the matching, okay? That for this time step, which was the fMRI vector, and which annotation does it correspond to? So if you can do that, you have some understanding of the fMRI response. So that's called decoding in the fMRI world. I would argue it's somewhat overselling. It's not decoding. It's some kind of a correlation. So all right, so that's what we did. Now I want to emphasize that this is not a typical applied math problem because there was no mathematical model for language, and so we replaced it with our representations of human language, the CIF vectors. And now you have a vector and a vector, and now you can try to correlate them, and that's what we did. There's a learned linear transformation that does that, and then it has actually a surprisingly high success rate in actually matching up fMRI with the language representation. And then my colleagues could carry out studies. You could look at that trained model and see where is this matching happening, which regions are more relevant, and so they come up with various diagrams like this, which I don't understand, expressing, relating where this understanding is happening in different brain areas. So this is, of course, the hottest trend in academia, apply machine learning to discipline X. And I hope that mathematics will join in this development. So concluding thoughts on ML, it starts with these very simple, naive-sounding questions. And it speaks to age-old mysteries. And it's a new way of looking at the world. It's different from classical physics, classical anything, I think. It's working with very complicated and inexact descriptions. And therefore, it's a new frontier for math, science, computer science. And I'm optimistic that current methods, which have been practically successful, can be mathematically understood or simplified. So thank you very much. And before you leave, there's this advertisement for various resources, including the special year at the Institute for Advanced Study next year that we'll be organizing. And if you're interested in participating, please send me a mail or look at the website.
So there will be
Turn it on.
there will be a reception in the math department lounge at after this talk. And so, any questions for this lecture?
Yeah.
Just the fact that you were saying that these deep models are capable of overfitting, does that mean that we actually want the instances to be ones in which the optimization doesn't succeed in the usual sense, meaning it doesn't
That's right.
find the global?
Not the global, yeah. And regularization has something to do with that. Regularization is that idea. Yeah. Yeah, in the back.
So, deep learning, what does the nonlinearity map into the non-convection of the
Oh, good. Actually, yeah. So even if you take out the nonlinearity, if you have a multi-layer model, even a linear model, multi-layer, okay, it's equivalent to a single linear model. But if you treat it as a multi-layer model, it's already non-convex. So indeed, yeah, you don't need nonlinearity for the non-convexity to emerge. But actually, the linear model is much more tractable mathematically. And I have a paper already and another one coming out in a couple of weeks which treats that. And other people have done that too. There was a question here. Any other questions?
So, thanks a lot. Thanks for the excellent lecture. Thank you.